Hey, good morning, guys and girls. So during the second part of class today, what we're going to do is use some ideas that we just tested on prior to the holiday and see if we can use those to identify some unknown characteristics of some various dyes, whether it be food dyes, whether it be dyes in pens, ink dyes, things like that. And to do that, I have to talk to you a little bit about something called chromatography. All right, so the lab we're going to do is called the Chromatography Lab. All right, we're going to take a look at ink dyes, specifically in this lab, in two different ways. In the first part of the experiment, we are going to analyze the ink dyes qualitatively, meaning non-numeric. What we're going to do is we're going to take a sample, piece of paper. We are going to put 6 different pens on that sample paper. So we're going to take pen number 1 and put it on dot 1, pen 2 on dot 2, pen 3, and so on. And all 6 of the pens seem like regular old-fashioned black pens. Then what's going to happen is we're going to punch a hole in the center of that piece of filter paper. And water is going to run through it from the middle out to the edge. And it is going to separate each of those dots into the various component dyes that make them up. Because what you're going to find is there isn't really just one dye in each of the pens. There are multiple. All right, varying colors, varying types of dye. That's going to create us kind of an index of the pens and what their signature is. Then what we're going to do is we're going to move on to an unknown. And the unknown has some number on it, which I will share with you when I send you your results. But what I have done ahead of time is I have used these pens to make 4 unknown dots. Right? So unknown dot number 7, maybe I used pen 3 for that. Unknown dot 8, maybe that was pen 6. Unknown 9, let's say it was 2. And unknown 10, let's say it was 5. We're going to go through the same process. You're going to punch a hole in it. Water is going to move out to the edge of the circular filter paper. And it's going to separate those pens into their characteristics. Now, to really understand what's going on with that lab, you have to understand what governs the properties that separates the pens. And that's where it ties into last chapter for us. Toward the end of the chapter, you guys learned about something called polarity. And we learned how to look at a Lewis structure that we drew, a dot line picture. And when we did that, we learned that we could analyze it to decide, is that substance polar or is that substance non-polar, right? And our rules for that were that if there were dots in the center atom, it is automatically polar. And if there aren't dots, we got to look at how it's pooled. If it's evenly pooled, it was a non-polar substance. It was surrounded by the same element. Or if it was an uneven pool, anyone on the outside is different, it would be apolar. Now, that is what controls how the inks are going to separate. Each of the different inks in the pen will be attracted to the water. And there's a principle that we're going to hit called like attracts like, or like dissolves like. And the more attracted to water you are, the further you will move with the water. So in any chromatography experiment, there are 2 phases. There is what we call the mobile phase, and that is the one that moves, and there is the stationary phase. And that's the one that stays still. And because like attracts like, and water is our mobile phase, because it's the thing that's moving, the more like the water that you are, the further you will go with the water. So the more polar you are, the more like water you are. Because if I drew you water, it looks like this. Those dots in the center atom, that makes water very polar. All right, so the more I'm like water, that particular dye component, the further it will travel with the water. All right, so that's what governs how far they move. Now, we can measure that numerically, and that's in part 2 of the experiment. But in part 1, we just want to pull the dyes apart into their different components. All right, and that's a matching game. You're just looking for what signatures over here match which signatures over here. All right, that's the whole idea behind the idea of chromatography. Now, I'm going to walk you through just a quick 101 of that again. Let me share my screen with you. And if we look at this, right, a bunch of different terms and definitions here. You don't need to copy this down, just walking you through what's happening. Right, so if you look at this, we have some sort of mixture. Your ink in your pen is a mixture. The food dye in your Kool-Aid, the food dye in your sodas, all of that, those are mixtures. They've got different dyes in them. So let's say hypothetically, we've got 4 components in our dye mixture. Right? We've got yellow, we've got blue, we've got white, and we've got red. Chromatography allows us to separate those things based on how attractive they are to what we call the mobile phase. All right, so it lets us analyze it. We can use it to identify, which you'll see in part 2. Sometimes we might use it to purify, right? We want to isolate one of those dyes, all right? And sometimes we might want to quantify, figure out how much of a dye is in there. All right, so like I said here, we have the mobile phase, which they call the mobile medium. It carries the components that are like it. And we have the stationary phase, the stationary medium. That's the part that doesn't move with the sample. So if I am like the mobile phase, I move a lot. If I'm like the stationary phase, I don't move much at all. So you're always getting like attracts like. It just depends on who you're attracted to, the thing that's moving, the thing that stays still. In our experiment, the water is the mobile phase, and the filter paper is the stationary phase. All right, so here's how this fundamentally would work. I would put a mixture sample on the bottom of the piece of paper. Then I'm going to put some liquid down in here, my mobile phase. Right? Capillary action is going to pull the liquid up the paper, just like if you put a piece of regular paper in water, the water will pull up the paper. The more like the water you are, the further you will go. So in this picture here, I know that the yellow is the most like the mobile phase because it moved the furthest. I know the red is the next most similar to the mobile phase, right? The white didn't move very far and the blue didn't move at all. That means they're probably more attracted to the stationary phase and less attracted to the mobile phase, which means the yellow and the red are most likely pretty polar, and the white and the blue are relatively non-polar. Right, if I showed it to you in real time, imagine we have 3 different samples. I put them in a beaker together, which we will do. I will put my mobile phase in there. I'm going to draw a line so that I know where my mobile phase started, because you're going to learn in part 2, we measure how far that moves. And then as the water works its way up the page, it will create various attractions to each of the dots here. So in this setup, blue is the most polar, the green would be second most polar, and the red would be the least polar if we used water as our mobile phase, because the water is a polar substance. If we use the non-polar substance as our mobile phase, everything would be backwards. All right, so mobile phase can vary, but for us today, we're using water for all of it. All right, so that's part 1 of the experiment. Right, and we're just trying to analyze the dyes. In part 2 of the experiment, We're getting much more specific. We want to figure out who exactly are the dyes. Yellow dye number 5 is one that you might know. Red 40 is a dye you've heard of. Some people are allergic to it. We want to know which dyes make up which pens specifically. And to do that, we have to get a little more quantitative. We have to calculate some numeric values. Right? And that numeric value is something called the RF value. All right, and RF stands for the retention factor. How do I calculate a retention factor? What I do is I measure how far the dye travels when we do this, and then I measure how far the liquid travels, the water that was carrying it. And those won't be the same because of varying attractions to the liquid. So let's say we took our dot. I put a dot here. We run the water up through this, and the water gets to right here across the top. We're going to let it go pretty close to the top. That right there is called the solvent front. The first thing we would do is we would measure how far that was. So we would start from where we placed our dot, which would be at this line, and measure to where the liquid went. That was there. And it moved 34.2 centimeters. That number will be the same for every single substance because the solvent moved that distance for all of them. What's going to happen to the individual dot is it's going to get pulled apart into various pieces. What we want to do is we want to see how far each of those pieces move. So you'll look at your dot, and you'll draw a line through the center of it, or you'll try to approximate the center of it. And in this one, we have 2 dots. Now, in your data tables, in your lab, I've put a lot of different boxes. It might say die 1, die 2, die 3, die 4, because I don't know how many pieces it'll break into. All right, so you may have empty boxes in your data table. If I was looking at pen 1, hypothetically, I would only have 2 dyes that I was filling things out. Then what I would do is I would measure how far the dye traveled. Right? Looks like it moved 8.4 centimeters for this guy. And for the green, he moved a lot further. He went 21.6 centimeters. That means I can calculate an RF value for each of those substances. The desolvent will be the same for both. The solvent moved 34.2 centimeters. Right? But the blue dye only moved 8.4. And the green dye moved 21.6. So we would go and get values for each of these yes, right? So the 21.6 divided by the 34.2, that would get me an RF of 0.63. So 0.632 for that. And then for the blue dye, 8.4 divided by 34.2, it has an RF value of 0.246. Now notice, these are always going to be decimals because the solvent front is always going to move the furthest. There's no way a dye can move further than the solvent. So the biggest number you could get would be 1 because the solvent front would carry the dot all the way to the edge, and that's all the further it could go. All right, so how does this help us? How does getting the RF value tell us what we need? All right, so if I share my screen again with you, what you'll see that I've done in the lab is I have shared with you a table that lists RF values of some dyes. hypothetically, I made these two dyes up. My blue one was 0.246. So I would scan through here, 0.246, and I see this guy right here at 0.23. Right, so I am going to assume that the blue dye is erythrocene. So I can identify the dye that made that up. The other one, 0.632, I would scan 0.632, closest one to that is this guy. Right? I would assume that my green dye, right, is carbamazine, right, by their RF values. So that's how you get the RF, and you're going to do it for all 8 pens of that experiment. So if you look at the data table here, notice I have left a couple boxes in each. For that first one, I might have 2 empty boxes. Then you can fill in the table based on what you're seeing. Eye color with the eye will be visual. You measure how far to that color. So if I were filling it out for pen 1, hypothetically, I would say dye 1, blue, dye 2, green, blank, blank. D dye, 8.4. D dye for the second line, 21.6. Then the RF value would be that little calculation over there. And then my dye name would be erythrocene and carbamazine. And you're going to do that for each of the 8 pens. And then here's your data table for part 1, which is filling in these things. So I'm going to take you to the back, and I'm going to walk you guys through what the setup for the experiment looks like to give you a feel for what you're doing. All right, so give me a second to carry it back here. And if I show you guys what's happening in the lab, right here is where everybody would start. You would come to the middle, and you would get yourself a piece of round filter paper. You would take that round filter paper back to your seat, which I will do. And I'm going to tip you down so you can see what I'm doing. You would then get yourself a pencil. And you would get yourself a series of pens, each that have a number on them, like that guy right there. It says pen number 6. Try to hold that to the camera. All right, so you'd come here. You would draw yourself a circle. And you would number 1, 2, 3, 4, 5, 6. Right? And that's what that would look like right there. Then what you would do is you would go and get each of the various pens, and you would place the proper pen onto the proper dot. So I'm taking pen 1. I put it on dot 1. Pen 2 on dot 2. Pen 3 on dot 3. Pen 4 dot 4. Pen 5 on dot 5. And pen 6 on dot 6. And then, like I said, what you'd do once you had those on there is you'd punch a hole through it. All right, and what we're going to do is we're going to create a little piece of filter paper that makes this look like a witch's hat. Right, and we're going to let the water run up through the sample. So what I would do is I would come to the middle counter. And just cut myself a square piece of paper, nothing on it. All right, then I would roll it so that it had a pointy end. And then I could put the piece of filter paper through it. Like I said, looks like a witch's hat. All right, then what I'm going to do is I'm going to take that sample and I'm going to put it into a beaker of water. All right. And when I do that, the water is going to run up through it. So I'm going to grab a beaker so you can see how that would start. All right, so here's my beaker of water. And I just put the sample in like that. And what you're going to see is that the water is going to start to come up through that filter paper, through that wick that's down here. All right, it's going up through, and then it's going to spread out through the dots. So the water is moving to the edges, like I showed you in the pre-lab. All right, so the parts of the ink that are like the water will get carried with it. All right, so I started a couple of those before you guys logged on. Here is what would happen after about 20 minutes. You would get this for each of the pens. So you can see there are different dye components in each. It has separated it into pieces. All right, now I'm going to share this picture with everybody. I'll take a picture with my phone, all right, and I will drop all of that into your emails and into the Google Classroom. All right, so I'm going to set that out to dry because I'll do it after we're done with the video. And then what you would do is you would get another piece of the round filter paper. All right, this time, I give it to you, and that has an unknown number written on it. Unknown 1, unknown 6, unknown 8. All right, there are 12. You're only getting 1, but I made 12 different ones. All right, so I had to run those as well, so this is kind of cool to look at. But here is the unknown column. So depending on which unknown I assign you, you will be getting a different result, which again, I will take pictures of all of those and I will send those with you. So for now, I'm just going to take those off so they can dry, because if I let the sample keep going, the water will wash the components that are like the water, the polar ones, off the edge. They'll just rinse it right off. So I need to get these guys off of the water bins before the water can carry the dye too far. So we'll give those a minute. All right, to dry. That's what part 1's all about. So for the first part of that data table, the 1 through 6, you guys will use the known picture that I send you. And what that's going to be is just a series of colors. You're writing colors in that table. Right? On that chart, it says center, middle, edge. So the center is where it is when it starts. The middle would be what it is halfway, and the edge is out here. So some of them made it to the edge. So you'll have colors in all 3. For instance, if I was looking at this one, I would say in the center it was red, reddish yellow. In the middle it was pink, and on the edge it was blue. But for this guy here, he never made it to the middle or the edge. So I would say bluish black, dash, dash for that one. All right, so it's okay to not have boxes filled in with the number because the non-polar ones won't move that far. You'll do the same thing for your unknown, whichever it is. And then what you're going to find out is on this one, hey, that bottom one looks a whole lot like this one now, if I make those line up, right? The one's facing down, and this is my known table. Hey, that's pen 1, which means this unknown right here, right, down right there, that must have been written with pen 1. That's the goal of the first part of the lab. Now, the second part of the lab, all right, what we did was we set up a square piece of paper, all right, and for that one, I came over here, cut out my square piece, and I did exactly what you saw in the pre-lab. I drew a line across the bottom. All right, that's where your water is going to start. And then I spaced out this time 8 pens. And then I put a dot on each of those with the same pens I did before. Then what I did was I rolled this guy like this, and I stapled him. And then he got placed in a different chamber because it's a bigger piece of paper. This guy here. And he's been running for a while, so he's ready to come out. So I can take this, tear it open, lay it flat. Now, the first thing I want to do on this guy is I want to draw a line right across where that water got to, because that is my solvent front. So I draw that line right there, and it's important to do that in pencil. Then what I'll do is I'll let this dry, and if we're looking at pen 1, I can see I've got yellow, I've got red, I've got purplish blue, and I've got a light blue. So I think there's 4 different dyes in there. So once this is dry, I would circle each of them like I did for you guys in the pre-lab, put a line in the middle of it, and then measure. So if I were doing this first one right here, I would circle right like that and put a line through the middle. I would circle the red, put a line through it. I would circle the purple, line through it. I'd circle the blue, line through it, which means I'll have to do 4 different RF calculations. All right, and you will do that for each of those. I will share this picture with everybody as well. All right, so that's the idea with chromatography. So what I'll do is I'll break you guys up into your breakout rooms with your partners. You guys will have till Friday to finish your report. 1 report per group is fine. You're sharing the same unknown. There's no reason you can't do the report together. All right. If you look at the format for the lab in the Google Classroom, share my screen with you one last time. What is it you need for the lab? Mostly the components. So I'll need a title, Chromatography Lab. Purpose, obviously we're trying to learn about ink dyes. And then we have 2 different data sections because we did 2 different labs. The qualitative ink lab, that's the circle filter paper lab. You'll have that data table, all right, including the number of your filter paper, which will be the picture I send you. The 2 chromatograms, again, those will be the 2 pictures that I send you. Just make sure you attach them. And then there's a series of questions I need you to answer based on your data. Right? Those are in the packet. The RF lab, which is the quantitative one, that data table filled in, the picture of the chromatography paper, which is called a chromatogram that I'm going to send you. And there's 7 questions with that, and then your 5-part conclusion. All right, so you work on that all period here with me when I have you, and then you can finish it up with the time you have left between now and Friday. And obviously, I'll be in the rooms checking in on you, answering questions, trying to help in any way I can. But the video should help, especially if you need to go back after the fact to try to figure some things out. I will see you guys soon. Thank you much.